It's kind of wild when you stop and think about it. You flip a switch and bam, a dark room is suddenly full of light. Your phone screen comes to life. It's this invisible power we use constantly, every single day, without a second thought.
But what is that stuff actually? What is really going on inside that cord to make everything work? Well, that is exactly what we're going to break down right now.
All right, so to really get this, we've got to shrink ourselves down. I mean, way, way down, past the plastic insulation and deep into the secret atomic world of the copper wire itself.
Okay, pop quiz. Take a look at these. One of them shows what the inside of a wire, what we call a conductor, looks like. The others are insulators. So which one do you think lets electricity flow? And if you picked B, you nailed it. See, what makes materials like copper so great for this job is that some of their tiniest particles aren't locked down. They're free to just wander around. And that one little detail, well, it's the key to everything. And this little free-roaming particle, it's got a name: the electron. This is the hero of our story, for sure, and the single most important thing to remember about it is its defining feature. It has a negative charge.
Now, that negative charge means every electron has to play by some very basic rules of the universe. It's actually super simple. Opposites attract, so positive and negative charges pull toward each other. But things that are alike, they push each other away. So two negatives repel and two positives do the same. That's it. That's the basic physics that runs this whole show.
Okay, so we've met our main character, the electron, and we know the rules of the game. But one electron isn't going to power much. So how do we get a whole stampede of them to move in the same direction, all at once?
Because left to their own devices, they just kind of wander around randomly. To get them organized and marching in a line, they need some motivation. They need a push. And that push comes from an energy source, like a battery.
And here is the absolute key idea. When we do get all those free electrons moving together in one big, coordinated stream, we call that an electric current. It's not about a single electron doing its own thing, it's about the flow of the entire group.
It really is that straightforward. I mean, the source material just nails it with this simple definition. The flow of current in a circuit is the movement of electrons around the circuit. That's the whole concept right there.
So we've got our electrons, and we know we need to get them flowing as a current. But a flow to nowhere is pretty useless, right? For that current to actually do something, like power a lamp, it needs a complete path to travel on. You can think of it like an electron superhighway. The whole journey has to start somewhere. For us, it starts at the power source. A battery is the perfect example. You'll see it has two ends, or terminals. One is positive, the other is negative. And that difference is what creates the push and the pull we need to get things moving. Next up, you obviously need the road itself. That's our conductor, the copper wire. It's already jam-packed with all those free-to-move electrons we met, all just waiting for the signal to go. But what's the point of a highway if it doesn't lead anywhere useful? The current needs a job to do. And that's where a component, like this lamp, comes in. The magic happens when the flow of electrons passes through it, causing it to light up. So when you connect all these parts together, the battery, the wires, and the lamp, so that they form one complete unbroken loop, you have officially built a circuit. Okay, so we have the power, we have the path, and we have the purpose. Now for the final and maybe most important piece of the puzzle. How do we actually control it? How do we turn it on and off?
This is where we get the idea of an open versus a closed circuit. The easiest way to think of it is like a drawbridge. When the circuit is open, there's a break in the path. The bridge is up. And the traffic, our electrons, they grind to a halt. But when the circuit is closed, the bridge is down, the path is complete, and the electrons can flow freely.
And you really have to remember this rule. It is the golden rule of electricity. If there is any break, anywhere in that circuit, everything stops. It doesn't matter how small the gap is. The entire flow of electrons just stops, dead in its tracks.
So let's put it all together. The moment you flip a light switch, what you're really doing is closing that break. You're completing the circuit. Instantly, all the electrons in the wire get repelled by the battery's negative end, and at the same time they're attracted to the positive end. This push and pull creates the current, which flows through the lamp and makes it glow. It's a beautiful, instantaneous chain reaction.
So let's just zoom back out for a second and connect all these little pieces back to the big picture we started with. It's incredible, isn't it? Everything we've talked about begins with that one tiny, negatively charged particle. But when you get trillions upon trillions of them all flowing together in a controlled circuit, well, you get this: a world that's lit up, connected, and powered by that simple, elegant flow.
From the lamp in your room to the device you're watching this on right now, it is all working on this exact same principle. Which kind of leaves you with one final big question, doesn't it? What will this invisible force help us discover next?